Journey today. We're heading to the edge, not of the universe, but of something you use every day, the number line. We're going to see what happens when you follow a mathematical path forever. We're exploring infinity.
You know, it's a question that just fills you with awe, right? The idea of traveling so far that you reach some kind of ultimate boundary. It's a concept that really stretches our imagination to its absolute breaking point.
But what if I told you that same kind of mind-bending journey exists right here, with just a pencil and paper? Yeah, that's exactly what we're doing today. We're going to travel infinitely far to the left and to the right on the number line and see what we find.
So how in the world do we actually do that? Well, in math, we've got this really powerful tool called a limit. And all a limit does is tell us what value a function is heading towards as we travel along its path forever and ever.
And this simple handwritten list right here, this is our treasure map. It shows us 8 different mathematical paths and where they end up at infinity. So let's bring this map to life, shall we? Our very first path is the exponential function, e to the power of x. Let's think of this one as a rocket ship. Point it one way, you get explosive, unstoppable growth. Point it the other way, and you get this super fast descent right back to Earth.
So, just like any journey, we've got 2 directions we can explore. One journey heading out towards positive infinity, and another one heading towards negative infinity. The question is, where does our rocket ship actually end up? Let's start by heading right into the positive numbers. And look at this, even at a pretty modest x equals 10, the function's value is already over 22,000. Wow, our rocket is picking up speed and fast.
Okay, let's really push the throttle now, all the way to x equals 100. And, whoa, the result is it's astronomical. That's a 1 followed by 43 zeros. The growth isn't just fast anymore. It's accelerating like crazy, just getting bigger and bigger with no end in sight.
And there it is. The destination is crystal clear. That confirms the first location on our map. As x travels towards positive infinity, our e to the x rocket just shoots upwards forever. Its limit is infinity. But what happens if we throw our rocket into reverse and travel the other way, to the left? Well, at x equals -10, the value is suddenly tiny. I mean, we're talking about an incredibly small fraction.
And the further left we go, the smaller it gets, just shrinking and shrinking, getting infinitesimally close to one single destination, 0. It never actually reaches it, but it gets closer forever. And that's our second limit checked off the list.
Now, what about the function e to the -x? Well, this is the easy part. It's literally just the mirror image of what we just saw. As we travel to the right towards positive infinity, it does the opposite. It heads straight for 0. And as we travel left, it's the one that shoots up to infinity. Just like that, we've covered the third and fourth destinations on our map.
Okay, time for our next function, the natural logarithm of x, or ln of x. Now, if e to the x was our rocket ship, think of the logarithm as a determined hiker. The climb is way, way slower, but the key thing is, it never, ever stops climbing.
So this hiker's path has a really strict rule. You can't take the logarithm of a negative number, or even 0. What this means is our journey to the left hits this invisible wall at x equals 0. We can't cross it. All we can do is get really, really close to it from the positive side, from the right.
So what happens at these 2 edges? Well, as our hiker gets infinitesimally close to that wall at 0, whoosh, the path just plummets off a cliff, heading straight down to negative infinity. But when we travel far to the right, that hiker just keeps on climbing. It's slow for sure, but it never levels off. It just keeps going up forever, towards positive infinity. And with that, we've ticked off limits 5 and 6.
All right, our final function today is a whole different ballgame. This is the inverse tangent, and its journey is so fascinating because, unlike the rocket or the hiker, this path actually has boundaries. It doesn't fly off to infinity. It's contained. To really get this, we need a new concept, the asymptote. And honestly, it's super simple. Just think of an asymptote as an invisible ceiling or an invisible floor. The path of our function will get closer and closer to this line, but it can never, ever touch it or cross it.
So for this inverse tangent function, as we travel way out to the right, it rises and then it starts to level off, getting closer and closer to that invisible ceiling. And you guessed it, as we travel to the left, it falls and levels off as it approaches its invisible floor. And here's the cool part.
These invisible boundaries are at very specific values. The ceiling, which is the limit as x goes to positive infinity, is pi over 2. And the floor, the limit as x goes to negative infinity, is negative pi over 2. And with that, we've explored the final two destinations on our map.
So we've done it. We've completed our journey to the edges of the number line. We've seen rockets and hikers and these weird invisible ceilings, but now we gotta ask the most important question: why does any of this actually matter outside of a math class?
And here it is, our completed treasure map. This table sums up everything we just discovered. You can see, clear as day, the destination, or the limit, for each function's journey to the left and to the right. This is the end behavior of each path, all laid out in one place. And understanding this end behavior is incredibly powerful. It's like having a superpower for making predictions about the real world. That explosive exponential growth? That's the model for a population boom. That slow, steady logarithmic climb? That's how we measure the power of earthquakes. And those functions with boundaries. They can model anything with a maximum capacity, like a chemical reaction that can only go so far.
So look, if you take one thing away from all this, let it be this. These limits, this handwritten list we started with, they are not just abstract rules to memorize for a test. They're dynamic. They're descriptions of a journey. They tell a story about where a system is ultimately headed.
And that's what is so exciting, isn't it? Today, we just brought 3 paths from that little map to life. It just makes you wonder,